So in this lesson, we are going to look at some of the evidence for how the Earth was made. Where did our Earth come from? Well, first of all, let's ask the question, how old is the Earth? The man you can see in the picture was called Bishop James Ussher, and he lived in the 17th century. And he tried to work out how old the Earth was, and he used the Bible. What he did was he looked through the Bible and he looked at all of the names of the old prophets and the people in the Bible, and he worked out who was the father and the son of who and so on, and went back and back and back and added up their probable ages, and he worked out, according to him, the Earth was made in about 4000 BC. In fact, he was quite precise. I think he said it was made at 4 o'clock on a Tuesday afternoon or something like that. So, according to Bishop Ussher, the Earth was about 6,000 years old. Well, by the 19th century, people realised that, this figure was probably quite wrong. And people were developing more scientific knowledge. So this man you can see in the picture here was Lord Kelvin. And in the 19th century, he used the science of thermodynamics to try and work out how old the Earth was. Well, thermodynamics might look like a scary looking word, but it's not really. Thermodynamics is basically about how heat moves from cold objects out into colder areas or colder objects. So thermodynamics is the movement of heat and how things cool down. And Lord Kelvin knew that the early Earth must have been very hot. So if you measure the temperature of the current Earth and you know how fast things cool down, it can help you to work out the age of the Earth. And Lord Kelvin, in his calculations, he worked out the Earth was between 20 and 40 million years old. So much older than what Bishop James Ussher had worked out using the Bible. However, we now think the Earth is much older than that, because Lord Kelvin was a very smart and a very hard-working man, but he did not know about something called radioactive decay. Again, that sounds scary, but at the level we're looking at, it's not really very scary. So, what happens is, in the early Earth, there was lots of uranium. If you have a look at the picture, this is a model of a uranium atom. Now, in a big piece of uranium, there are billions and billions of atoms, and every now and then, some of those atoms, it's called decay. They split up into smaller atoms, and when the big uranium atoms split up into smaller atoms, they give off a lot of heat. So radioactive decay in the early Earth created a lot of heat and kept the Earth hot for a very long time. Some other piece of evidence which tells us that the Earth was very old is that scientists have found small crystals of something called zircon, and these crystals are, some of them, more than 3 billion years old. So nowadays, using all of the evidence, scientists are now worked out, they think the Earth is now about 4.5 billion years old. So obviously, if you remember, the universe was nearly 15 billion years old, extremely, extremely ancient. But the Earth also very ancient, 4.5 billion years old. Well, how did the Earth and the solar system and things form? In space, you have massive clouds of gas and dust. And sometimes gravity will pull the dust and the clouds of gas together, and as they get pulled together, they get thicker and thicker and denser and denser, and usually when things are pulled together in space, the gravity pulls everything to the middle, so it wants to form a sphere, it wants to form a ball shape, and when the gas gets pulled together and more gas gets pulled in the middle of that sphere, all the gas being pulled in from outside is pushing and pushing into the middle of that sphere, and it gets hotter and hotter and hotter with all that pressure of the gas pushing down, and when it reaches a certain point, a star is born, because the heat starts off a big scary chemical nuclear reaction in the heart of it, and you get a new star. Well, often those new stars are spinning around, and around that spinning star you have a big disk of gas and particles of dust and rock. And that's what the Earth and the other planets formed out of. So there's a spinning disk of dust and asteroids and gas around the sun. And the bigger ones form together into meteors and asteroids, and some of those hit and they combine and they form bigger ones and bigger ones and bigger ones, and the bigger ones hit other ones, and so gradually they combine and grow into these large things that we have today called planets. And our planet, the planet Earth, I say again, scientists estimate was formed about 4.5 billion years ago. And at first it was a very hot, molten Earth. Molten is when rock is so hot it flows like a liquid. Then, after some time, the oceans arrived around, and scientists aren't really sure. There are different theories, different ideas about this. Some say before, some say after. But around 4.5 billion years ago, the crust of the Earth solidified. So it wasn't liquid rock anymore. You had solid rock on the surface. And there was some water vapor, some steam already in the atmosphere, the thick atmosphere of the Earth. But one theory at the moment, not all scientists agree, some disagree with this idea, but some think there's lots of evidence that asteroids and comets hitting the Earth, containing water, they also brought in more and more water to the early Earth. And so it's possible that some of the Earth's water and its oceans came from space inside meteorites. This early Earth, many billions of years ago, would not be a very nice place to live. The surface temperature was about 230 degrees. But even though it was so hot, much hotter than the temperature which water boils at on Earth today, the atmosphere was so thick and heavy and pressing down so hard that although the seas were so hot, they couldn't boil. In fact, the oceans were also not like the oceans today. They were green. They had lots of iron in them, which made them a green colour. And all this thick atmosphere was full of carbon dioxide, CO2, which made the skies look red. So green seas and red skies and very, very, very hot. In fact, if you were to go back in time, you'd get squashed flat and burned very quickly. So if you have a time machine, don't do it. Let's have a look now at two different kinds of rock, which are basaltic and granitic rock. Well, basaltic rock was the first form of rock to form on the Earth. And it's a bit heavier, it's a bit denser. Several billion years ago, volcanic activity in the oceans mixed with something called the magma, which is the liquid rock under the Earth, and you got a lighter form of rock, a less dense rock called granitic rock. So because this granitic rock is less dense, have a look at the diagram. You can see the red hot magma, that's the liquid rock, and above that there's a layer of basaltic rock, and then on top of that you've got this granitic rock. So basically the granitic rock, because it's lighter, it floats really almost on top of the basaltic rock, and because it's higher up, it sticks out of the oceans. So under the oceans you have basaltic rock, and we live on the continents, and the continents are made out of granitic rock, the lighter granitic rock. Something else about the Earth is nowadays scientists are largely in agreement. There's lots of evidence that for something called tectonic plates. Well, the theory was first put forward by a guy called Alfred Wegener back in the 1920s. And Alfred Wegener noticed something that lots of people have noticed over time. If you look at South America, it looks like it would fit in nicely with Africa. If you brought it over, the two would fit together. It looks like before, a long time ago maybe, they would join together. And that's what Alfred Wegener came up with. He said, look, the continents are moving. I'm finding evidence for this. Well, basically, lots of people, famous scientists, respected scientists, they laughed at Alfred Wegener. They said, what a ridiculous idea, Alfred. Obviously, the continents have been in the same place forever. Your idea is stupid. Well, over time, Alfred Wegener was proved right, although unfortunately he died in a snowstorm before he knew that people widely accepted his idea. And basically what happens is that tectonic plates, they basically float on top of the liquid rock underneath, and they have joins between these plates. Can you see the join here in between America on the left and the Eurasia and Africa on the right? Well, currents in the magma, just like in boiling water, it rolls around and boils around. Under the earth, you have this liquid rock and it moves around in currents. And this moving current of rock under the earth causes the tectonic plates to move very, very slowly. So as you can see in the picture here, Africa and Eurasia are moving away from the Americas. Okay, so there you see it. Africa and Eurasia moving away from the Americas. Very, very slowly. In fact, in your lifetime, if you live a long time, they'll probably move about 2 meters. Okay? Here you can see a little bit more detail on that. If you look at F in the middle, like I say, under the surface, that liquid rock is rolling and boiling very slowly. And the areas where it comes up, you get these volcanoes, often under the sea. And it creates new rock. And the movement, if you look at E here, the movement of that liquid rock moving under the surface, it makes the rock on the surface slowly move apart away from the middle where the hot rock's coming to the surface. And so here, for example, if we go back one, you can see this is the join in between the 2 plates, between the Americas and Africa and Eurasia. So new rocks being created, and these continents are being pushed apart by the drifting rock underneath. So let's move forward.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in 2 directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down.
So that's very simply, explain that again. Now let's have a look at something called stromatolites and oxygen. These things were very, very, very important in the history of the early Earth. And without them, you and I would not be here. Basically, you have bacteria. You had bacteria in the early Earth. And the bacteria form, can you see these strange lumpy things in the picture? These are made out of the waste products of the bacteria. And what the bacteria did, if you remember, the early Earth would be very poisonous to us today. It had a very thick atmosphere with loads of CO2, not much oxygen at all. Well, basically, the bacteria on these stromatolites used that carbon dioxide, used that CO2 together with sunlight, and it produced oxygen. It took the oxygen out of the carbon dioxide, it used the carbon to help make its body and the sunlight to give it energy, and it gave off oxygen. So it used up CO2, took all of that, a lot of that heavy CO2 out of the atmosphere, and it gave off oxygen, the oxygen that we breathe today. That's called photosynthesis. And basically what happened is, over time, it took many billions and millions of years. Over time, those red skies became blue because of the oxygen, and the seas also became blue. That iron was taken out of the seas, it rusted away and drifted to the bottom, and the seas became blue. Okay, so I hope you've made some good notes there. Let's have a quick summary of the information. So the Earth was formed by meteors hitting and combining about 4.5 billion years ago. Some scientists think that some of our oceans may have come from space. Many meteorites and asteroids are about 5% water. Radioactive decay, uranium splitting into smaller atoms and giving off heat, may probably have kept the early Earth warm for a very long time. Basaltic rock is under the oceans, and the newer granitic rock, which is lighter, that forms the continents, which so basically float on top of the basaltic rock. And we have tectonic plates. The continents are sitting on tectonic plates which are slowly moving on top of the magma which is flowing underneath. So good luck with that, and I hope that you get a good score in the quiz. Good luck.